All right, well, ladies and gentlemen, welcome here. We're going to start things off by considering something like this here. So I've got my diagram like this, and I've got, here's 4, this is 3, and we got two 30-degree angles here. So the first thing to ask ourselves is, do we have similar triangles? Now, considering how the picture is set up here and the fact that I'm not trying to mess with you here, right? AE and BD here appear to intersect at C, and it appears like we have ourselves some congruent angles like so. We can go ahead and fill that in. So it looks like I've got a pair of angles on top here, right? This 30-degree and this vertical pair of angles, so that does seem like it should work out. So those are indeed similar triangles, and it seems like we have angle-angle postulate here to guarantee us that these are similar triangles. Okay, that seems pretty fair. Now, if angle ACB measures 60, we should be able to fill in everything else here. So this is 60. That tells us that DCE is also 60 as well. And we know, therefore, that this is 30 and 60. Therefore, the last side is a 90-degree angle. So that means we can figure out the last angles here are both 90. And we got ourselves two 30, 60, 90 triangles. So this is 4, this is 3. This is going to be, now we can fill in everything here. AC is 8, CE is 6, right? And we know that the long leg is radical 3 times the short leg. So this is 4 radical 3 here, sorry. And this is 3 radical 3 here, right? So we can kind of fill that in. Okay. So what I'm going to do, ladies and gentlemen, is I'm going to focus on this 30, 60, 90 triangle bit. And we're going to see what's going to go on here. I've got two triangles like this, so let me go ahead and redraw them so they actually look similar here, right? One thing about these similar triangles is that you can always very easily redraw the triangle so that they look like they're in the proper positions here. So I have, here's ABC here. This was 4 radical 3, this was 8, and this is 4, right? We know that this is going to be similar to another triangle. In this case, I have another triangle here. So in this situation here, this looks like D, this looks like E, this looks like C here. So we have a 30, 60, 90 triangle yet again. This is 3, this is 6, this is 3 radical 3 here, right? And you know what? Just for the hell of it, I'm going to throw in another triangle here. I'm going to toss in a general triangle like so. So this triangle will be in red. It's going to be a general triangle, but I want it to be similar to the others. So if it's similar, that means, one of the things about the similar triangles here is that let's call this FGH, right? We want to make sure that all the angles are the same. So here's, again, we have the corresponding angles matching, and the corresponding sides should be in proportion. So we can have here our x, 2x, x root 3 here, right? Okay. So now I want to focus on this set of triangles here. We'll kind of take a look at these things. One of the important things about similar triangles is that we know that the corresponding sides are proportion. Therefore, I should be able to write several proportions here involving the sides. So for instance here, let's take a look at this. So there are certain things that will always hold up. So for instance, this 30-degree angle on top here, we know that BC, for instance, BC to AD, right? We can write that BC is equal to 8. So BC over AD here, we know is going to be equal to, well, not AD. Let me use AC instead. AC. There's going to be a 4 to 8 ratio, right? And that's just 1/2. Now, there are halves that appear everywhere else as well, right? So you see there's a half here, but there's also halves in the other pieces as well. So for instance, in this case here, this is going to be DC over EC here. That's also 3 to 6, which is 1/2, right? And in our red triangle over here, we have the same idea. We kind of have this sort of thing, GH over FH here, which is a x to 2x ratio, which is 1/2, right? So notice that there's this 1/2 thing going on here. Now, you may be thinking to yourself, that's nothing special because that was something we knew about 30, 60, 90 triangles. But that does tell us something important here. That tells us that this is something intrinsic to this specific angle, this 30-degree angle up here. Because if you think about what's going on, we have a right triangle here, right? If you know there's a right triangle here, there's a 30-degree angle up here, that third angle, the angle on the bottom, is locked into place. So we actually know that here. This means that there's something about this 30-degree angle and this 1/2 that seems to really, that seems to be related with one another. And that's going to be important to us later on. Furthermore, there are other ratios here that seem to work out in addition. So we have BC to AC is that 1 to 2 ratio here, right? Note that there's also another ratio here as well. So let me look at AB and AC, right? If we look at this value, AB and AC, this is just 4 radical 3 over 8, which is radical 3 over 2, if I'm not mistaken, right? So we kind of have this sort of thing here. The same is going to occur in each of these other triangles. So in this situation here, we can say that ED over EC is 3 root 3 over 6, which is 1/2 here. And then in this situation, we have GH over FH. So we had GH over FH. Now we can take a look at it and write this as FG over FH here, which is x root 3 over 2x, which is, again, rad 3 over 2. So, again, we have this constant thing here, this radical 3 over 2 that keeps popping up over and over again. And that's going to be important to us as we go, right? And, we can actually continue with this even more. We can say there's another ratio that pops up here as well. Now, note that in this situation, we're just comparing two sides of the triangle here. So technically, if you think about it, since there are three sides of the triangle, we're comparing two of them at a time, and the order is going to matter because you can just flip over the things, it should be 6 possibilities here. We're only going to focus on 3 of them because the 6 ratios are actually going to be in 3 pairs. So we can write this as BC over AC, but we can also write as AC over BC here. We get so that we have a 1 and 2, 1 over 2, and 2 over 1. For the most part, they're going to remain the same. So I'm going to focus on it one at a time. So one final thing I can do here is I can focus on, in this case, BC over AB. So notice how we have BC over AB. So in this case, this is 4 divided by 4 radical 3 here, which is 1 over rad 3, right? Same thing is going to occur here. We have DC over ED here, which is 3 over 3 radical 3, which is 1 over rad 3. I know technically we shouldn't leave the radicals in the denominators, but I'm just doing this here to show something. And we have GH over FG here, which is x over x radical 3, which is, again, 1 over radical 3 here. So notice that, and by the way, since this red triangle was general here, this worked on, so the key with this is that this works on every triangle that's similar to these 2 original blue ones. And since we are assuming that we have right triangles to start off with here, this means that each of these values, 1/2, radical 3 over 2, 1 over radical 3, all of these values here are actually intrinsically baked into the 30 degrees, which means that there's some aspect of the 30 degrees here that's going to help us out here. And this is sort of the rationale and the idea behind this is sort of an introduction, a very gentle introduction to something that we refer to as trigonometry. And each of these ratios here we actually define. So for instance, in this situation here, we actually define something like this here. Notice how in each of the cases, BC, DC, GH, these are all the legs. If you look at the 30s, these are all opposite the 30-degree angle here. So in this situation here, right, if we take a look at each of the rows, this here, this is opposite the 30-degree angle. And then AC here, AC, EC, and FH, these are all the hypotenuses of our triangles. So this is our hypotenuse here. Okay, so you have opposite the 30-degree angle here, and you have the hypotenuse here, right? Similarly here, with the AD, AB, ED, and FG, these are the sides that are adjacent to the 30-degree angle. So this is adjacent to the 30-degree angle here over hypotenuse, right? The denominator of the ratio didn't change. We still have our hypotenuse thingy here. And now we can kind of do the same thing down here. We know that BC is the opposite, ABC adjacent, so I can write this as opposite the 30-degree angle over adjacent to the 30-degree angle here, okay? And each of these ratios here is defined in a specific way. So the fact that all these ratios are the same means that we can actually define these ratios and give them specific names here. So I'm going to be introducing these things to you folks. So each of these 3 ratios here, the first ratio here, this one here, we refer to as what is known as sine. All right, there we are. So we can say the sine of an acute angle of a right triangle is the ratio of the length of the side opposite the angle to the length of the hypotenuse here. So we can kind of have this sort of thing here. So by the way, ladies and gentlemen, this here, you see sine A. This A here, this is an angle here. And sometimes you'll see this in parentheses. There could be parentheses around the A here. It doesn't have to have the parentheses around the A, but you can have this sort of thing here. We refer to this as the sine of an angle here. Even though this is read, even though it looks like sin, we read this as sine, S-I-N-E. It's the side opposite the angle divided by the hypotenuse, which in this situation is opposite of our hypotenuse here, okay? Right, so this here is the first of these ratios here, going back to this. Opposite the 30 over the hypotenuse. Opposite the 30 over the hypotenuse here, okay? By the same token, we can define the second of our ratios. The second thing we're going to define is what is known as the cosine. So this here we call the cosine. The cosine of an acute angle of a right triangle is the ratio of the length of the side adjacent to the angle to the length of the hypotenuse here. So we have this sort of thing going on here as well, ladies and gentlemen. Sorry about that. Let me just make sure that this is clear so we can see it. Okay? So we have this sort of thing going on here. And going back to our picture, in this case, it's the side adjacent to the 30 like this, the leg adjacent to the 30 over the entire hypotenuse here. So AB over AC, ED over EC, FG over GH. Okay? And then finally, the last one here, we define as what is known as the tangent. So I'm going to go ahead and move that up here so we can see this. So we refer to this as known as the tangent. The tangent of an acute angle over a right triangle is the ratio of the length of the leg opposite the angle to the length of the leg adjacent to the angle. So you want to make sure that you that these definitions are there. These are the definitions for these particular ratios here. We define the ratios in these cases here. So everything that we're going to be looking at in a right triangle is only going to focus on these particular definitions here. So keep these in mind. You're going to be needing these, and we're going to be using these throughout here. So as long as you understand these, you're going to be in good position here. You're going to be just fine. Okay? So we define this idea here of tangents and all this other good stuff here. Keep this in mind because this is going to be useful as we go through the very basics of trigonometry as we do this. Okay? So we have ourselves our sine, cosine, and tangent here, right? So I'm just going to review really quickly here. The sine, again, opposite over hypotenuse like this. The cosine here, adjacent over the hypotenuse is this. And then the tangent is opposite over adjacent like that. And you should be just fine.